Okay, thanks a lot. And thanks a lot to the organizers. This has been a really great week, a lot of fun. So I'm going to talk about a paper from the spring with Nima Fkemijedi, Henry Cohn, and Amir Tajini. There was a simultaneous paper by Alex Maloney and Edward Witten, and this talk is coordinated with Alex's talk, which is coming up next. So well, I guess the main idea in these two papers was sort of the same, but everything else about the two papers is different. So that that's their only point of overlap, and that's why we felt that we could give two talks about it. So we've coordinated this to entertain you for two talks worth. So the proposal that we both considered is the following. So consider n-free bosons in two dimensions. This is a CFT with n squared moduli, show the moduli of the toroidal conformal field theory. The proposal is that the ensemble average of this CFT is holographically dual to an exotic theory of three-dimensional gravity. There's really sort of gravity in quotes. On the boundary side, we have these n-free bosons averaged over moduli, and the proposal for the bulk theory is a u1 to the n by u1 to the n Chern-Simons theory. So these are the left and right Chern-Simons gauge bosons summed over topologies. This is we call this theory u1 gravity, and I'll describe it in some detail. So in this talk and in our paper, we discuss the torus partition function. So in particular, we're going to discuss this part of the duality that says that if you take this CFT partition function and you average over moduli, then it agrees with this bulk theory summed over topologies. And so we'll talk about the spectrum and the theory on a torus. I'm going to start with some background on the free boson CFTs or the Narayan CFTs. So this is the theory of n-free bosons in two dimensions. There's a target space metric, G, and a target space B field, B, which altogether make for n squared moduli. This is a conformal field theory with central charge C equal to n, the number of free bosons. And the conformal field theories of this type are famously related to Narayan lattices. So the partition function of the free boson or Narayan CFT is we can, instead of specifying G mu nu and B mu nu, we can specify a Narayan lattice. So this encodes the same set of data. And the partition function of the CFT is 1 over eta squared, sorry, eta to the 2n, times a sum over lattice vectors. So P bar live in this Narayan lattice, and the conformal weights are determined by the vectors in the lattice. So a Narayan lattice is an even self-dual lattice, in this case in signature n comma n. To orient ourselves, the simplest example is a single compact boson where we sum over momentum and winding. M and n are momentum and winding. There's a modulus, which is the radius of the target circle. And the Narayan lattice is a two-dimensional, in this case, is a two-dimensional lattice where we package the momentum and winding into this two-dimensional vector. So all Narayan CFTs have at least a current algebra, which is u1 to the n by u1 to the n. That's n currents, n left-moving currents, and n right-moving currents. They can also have enhanced symmetries. So there are points in moduli space where the symmetry algebra is bigger than this, but this is the symmetry algebra that's present everywhere in moduli space. In this formula for the partition function, the Dedekind eta functions out front account for the descendants under this algebra, under u1 to the n by u1 to the n. And you can see that just by expanding out the eta function. So there's the denominator here if you expand this out, just gives counts the modes of the current that you get dx from the free boson. So the eta functions are accounting for the U1 by UN descendants, and that means in the partition function sum, the points on the lattice lambda correspond to primaries under this algebra, under the U1 algebra. And when I talk about this U1 algebra, when I talk about the algebra, I'm always going to be talking about this one, the U1 to the n by U1 to the n, that's present everywhere in moduli space. So the points on the lattice are primaries. And if we have a point p comma p bar, this is, I split the points this way because remember this is signature n comma n. So p is a vector associated to the plus, yes.
Apparently there's some part of your slide that is invisible by a gray block. Can you try to like restart screen sharing?
Okay, which is it? Maybe it's where my video is. How about now?
Yeah, it's possible as you move it around, like there's something happening. Now it's better, but there's still like okay, it's worse.
Okay. Let me how about now?
No, it's like at another place, but still blocking part of the screen.
I think you need to stop sharing and reshare.
Okay.
Yeah, so we can try it.
How's that?
Right now it looks good.
Okay.
Go ahead.
All right. So these points on the lattice are labeled p comma p bar because the first vector is a vector in Rn that's associated to the plus piece of the metric, and then the p bar is associated to the minus components of the metric. So given this point on the lattice, the scaling dimension is p squared plus p bar squared, and the spin is p squared minus p bar squared. So these theories have moduli space. To get the moduli space, we can use the fact that actually all Noreen lattices of dimension n are related to each other by rotations, by O(n), n rotations. In other words, there's a square Noreen lattice, and starting from the square Noreen lattice, you can act with O(n), n rotations and get all of the other Noreen lattices. So the moduli space of Noreen lattices is almost O(n), n. That's not quite right because there's the reshuffling, the usual discrete transformations that reshuffle the lattice vectors while preserving the lattice. That's the T-duality group O(n), n, z. So the moduli space of lattices is O(n), n divided by this O(n), n, z. But then there are also the individual O(n) rotations on the two plus and minus subspaces, which don't affect the conformal field theory. So the moduli space of Noreen CFTs is isomorphic to this quotient written here. Again, for orientation, if we're talking about a single compact boson, the modulus is r, the radius of the target circle. And the moduli space is, since it's under T-duality, sends r to 1 over r. So the moduli space in that case is just the segment of the line r greater than or equal to 1. So now I'm going to turn, so this is just a review of old things that we learned in string theory. Now I'm going to turn to averaging over lattices. First, why should we average? Well, there's a lot of answers for this. In hindsight, I think the best answer is that it gives an interesting answer that we're going to see has a holographic interpretation. But actually, that was not our motivation. So I want to tell you how we came at this problem. I think that would have been a good motivation. It would have been very reasonable to say, well, given everything that's happened in holography, we should average CFTs, and here's one we can try. But that's actually not what we did. So what actually happened was we were studying modular bootstrap bounds on the spectral gap in various theories. So in modular bootstrap, the goal is to place bounds on the dimension of the first non-trivial primary, delta 1. And this has a lot of interesting connections to holography and 3D gravity. But we were studying it for the case not of the Virasoro algebra that people usually study, but for theories with a U1, with these U1 to the n times U1 to the n current algebra. The reason we were studying that problem is because with this chiral algebra, the modular bootstrap gives constraints on sphere packings. So there's this correspondence between modular bootstrap with this algebra and sphere packing. Now, that correspondence applies to modular bootstrap constraints in what's called the spinless modular bootstrap. So that's constraints that you get from studying the partition function at 0 angular potential. But since that gave these interesting connections to sphere packing, we decided to study the modular bootstrap with spin, that is to study the full constraints. And we started looking at this problem of trying to understand how large delta 1 could be when you impose the full constraints of modular invariance. It turned out that that's not related to sphere packing. So that's why I'm being brief about this. Nothing for the rest of this talk, nothing that I'm going to say is really related to sphere packing. But it was in the process of studying this that we came across averaging, and it was very natural in this context because in the theory of lattices, actually averaging is a standard trick in the literature to derive bounds on the spectrum in a large number of dimensions. So if you want to understand how, in the language of lattices, we're talking about lattices with a short vector, whose length is determined by delta 1. And in the theory of lattices, this is a standard trick to average over lattices when it's hard to actually construct examples in large dimensions. It's easier to study the average. So this is a trick that was introduced by Siegel, and this is what led us in this direction. But let me just proceed and talk about how this averaging is done. Okay, so the moduli space of n-free bosons, we said, is this quotient. To average over moduli space, the natural metric to average over, the natural metric to use is the Zamolodchikov metric. For free bosons, this is the same as the Haar measure on O(n), n. So this is determined by symmetry, and this is the natural metric to use. So we're going to average with respect to the Haar measure. Let's define the average partition function. So the average partition function, which is denoted with these these double brackets, is an integral over moduli of the Narain partition function that I had up a couple slides back. It's integrated over moduli with the Haar measure, and this is an average, so we divide by the volume. This integral converges for n greater than 2. Okay, so we're going to talk about the case n greater than 2. This average was actually calculated by Siegel back in 1951, and I'm going to spend some time reviewing how this calculation is done in the next couple slides. But first, the answer. So in CFT language, Siegel's result for the average density of states is as follows. So rho L of delta is the density of states at spin L and dimension delta. So L is an integer, delta is continuous, and here's the density of states. Okay, so this function of delta squared minus L squared to a power, and there's a complicated coefficient with some number theory going on here. You can see zeta function, sigma here is the divisor function. So this is the answer that he got. What I've done is I've averaged the partition function and rewritten that as a statement about the spectrum of that averaged partition function. So there are a few things to notice in this formula. First of all, the answer is continuous. Delta here is obviously continuous. It's not in any individual CFT, this would just be a sum of delta functions. But in the average, it's of course continuous. And that's to be expected because we're averaging over moduli, and that's moving all the states around and giving us a continuous spectrum. Secondly, it extends down to the unitary bound. So the unitary bound is delta greater than or equal to magnitude of L. And this spectrum has support all the way down to the unitary bound. Finally, it has a vacuum state. Obviously, it has a vacuum state. The vacuum state here is the delta function. And that's also to be expected in contrast to, say, a non-compact conformal field theory, where you would get a continuous spectrum, but no normalizable vacuum state. In this case, you get a continuous spectrum and you get a vacuum state because every element of the ensemble has a vacuum state. Okay, so I want to explain briefly how this is calculated.
There was a question. There's still a question because the hand was removed from Daniel. Okay, apparently not. So sorry, please go ahead.
Okay. Okay, so I want to sketch how this is done. It's a beautiful argument, and it starts as a nice warm-up problem. We're going to look at averaging over Euclidean lattices. The case of Lorentzian lattices, Narain lattices, is a little bit more complicated, and we'll see why in a minute. So we're going to first average over Euclidean lattices of unit determinant. The moduli space of Euclidean lattices is just SLNR mod SLNZ. So these preserve the unit determinant. And the claim in this case is that the average density of lattice vectors is given here. Rho of x is a delta function plus 1. In other words, the average Euclidean lattice is just the uniform distribution plus the point at the origin. So here's the proof, which is due to Siegel. The Euclidean space Rn has 2 orbits under the symmetry, under SLNR. It has the origin. The point at the origin is the first orbit, and the second orbit is everything else. In other words, you can get from any point in Rn to any other point in Rn by an SLNR transformation. What that means is that we can immediately conclude by SLNR invariance that the density of states is the sum of 2 terms. We have to put on each orbit, the density of states is fixed by symmetry. So we have to put the SLNR invariant measure on the origin, which is just a delta function, and the SLNR invariant measure on everything else, which is just the unit measure. So symmetries alone fix the density of states on the 2 orbits to look like this. And then we can fix the coefficient. Now all we have to do is fix the coefficients. The coefficient of the delta function is obviously 1 because every lattice has a point at the has 1 point at the origin. To fix this second coefficient, we use the asymptotics. So a lattice with unit determinant will have, on average, 1 point per unit volume if you go to very large scales. So if we look at the asymptotics, this has to asymptote to 1, and that fixes the second coefficient and proves the claim above. The argument for Narain lattices is similar, just we'll see it's souped up a little bit. So for Narain lattices, what makes it complicated is that now there's an infinite number of orbits under the symmetries. So let me explain that. Remember we said that the points on the lattice correspond to to primary operators with this value, with this dimension delta and spin L. If we act on the theory, if we act on the moduli with O(n), n, this preserves the spin, okay? Because the spin here is just the O(n) and n, n invariant inner product. It's the inner product with n pluses and n minuses. So acting with O(n), n does not change the spin. And that means that each value of the spin is an orbit of this symmetry action. So if I draw the spectrum, if we view the spectrum as points in this space labeled by the vectors p and p bar, then there are hyperboloids p squared minus p bar squared equals 2L. And each of these hyperboloids is invariant under O(n), n. So there's a hyperboloid at each spin. And as we act with the symmetries, we just move points around on the hyperboloid. These are hyperboloids in this Rn, n dimensional Rn, n space. And you should think of the radial coordinate on the hyperboloid. So each hyperboloid is labeled by spin and has radial coordinate dimension, delta. So now we can do the first step of Siegel's argument, which is to use symmetry to fix the answer on each symmetry orbit. On each orbit, the density of states has to be just given by the standard volume measure on the hyperboloid. So we just calculate the volume measure on these hyperboloids, square root g, and rewrite it in terms of the radial coordinate delta. And this is what you find. There's a one-line calculation that gives you this measure. So this is just the usual volume measure on hyperbolic space with this signature. So this gives us the answer that we're looking for up to a coefficient. The answer that we're looking for rho L delta, remember it was this factor, this function of delta times this complicated coefficient with zeta functions and divisor function. So we now have fixed it up to a coefficient, and all that remains is to calculate that coefficient. I'm just going to do this slide very briefly. The point is just that you use the asymptotics. Okay, so we've calculated this density of states up to a coefficient, and now we can determine the coefficients using the asymptotics. Let me skip the details of some of this in view of time and just say that this can be done various ways. I think the one simple way to do it is using modular invariance. So you run through what's essentially the Cardy formula or the Cardy argument to calculate the asymptotic density of states. And what you find is that you have to do an inverse Laplace transform that's dominated at the cusps of SL2Z on the tau plane. So it's dominated at the real rational values of the modular parameter tau. Then you use modular invariance to evaluate the partition function near the cusps and sum over these and sum over coprime A and B to add up all the contributions from all the cusps. This is very similar to the usual derivation of the Cardy formula in CFT, except that in a theory with Virasoro symmetry, it's a little bit different. In a theory with Virasoro symmetry, you only have to include one cusp, the one at 0. And that's because in a theory with Virasoro symmetry, the other cusps are exponentially suppressed. But in a theory like this one that has UN symmetry, or U1 to the N symmetry rather, you have to add up all the cusps. And when you do that sum, so you add all this up, and that gives you this coefficient that we were looking for, and leads us to the formula that I gave a few minutes ago, Siegel's answer for the average density of states on an array lattice. So that's the calculation that gives this result here. Now we're going to study this and try to make sense of it. First, I want to mention the spectral gap. So let's look at the spectral gap of this theory. Remember, delta 1, the spectral gap, is the scaling dimension of the lightest non-trivial primary. Now, strictly speaking, this density of states goes all the way down to 0. So strictly speaking, the gap of the average theory is 0. But I don't think that's quite the right way of thinking about it, because for large n, the low-lying density of states is much less than 1. So in fact, most Narain CFTs have no light states. And you can see that from this formula just by looking at the exponent here, that if delta is small, then we raise it to a big power, then we get 0. So a better way to define the gap in the average theory, yes?
Alex has a question.
Go ahead.
Yeah, quick question, Tom. How do I see the Cardy formula in your expression here for the density of states?
Well, this is the density of primaries, so you can't immediately see the Cardy formula here.
Sorry. Okay, this is density of primaries. Okay.
Yeah. I'll mention I'll have more to say about that in a minute. Okay. So a better way to define the gap is to look at the not where the density of states is non-zero, but where it becomes appreciable. So where it actually has a lot of states. So we can define it this way. And then if you look at this formula at large n, you find the gap is at n over 2 pi e. So to somebody who studies 3D gravity, this sets off some alarm bells, because this is a surprisingly large gap and suggests, sorry, is it back? Sorry, my screen sharing stopped, but I guess it's okay. So this is an interesting answer because it's large. It grows with n. And this is what suggested to us to look for a holographic dual. Because remember, initially we were just studying the modular bootstrap and looking to understand what delta 1 looked like. But this is a really interesting answer. To make it even more interesting, note that this is in fact the Cardy threshold for a theory with U1 to the n symmetry. So what I mean by that is the following. The Cardy formula, well, the usual Cardy formula applies to theories with a Virasoro symmetry. If you rerun the argument for the primaries of a theory with U1 to the n symmetry, then this is what you get for the Cardy formula. So this logarithmic formula. And this again has spectrum all the way down to 0. But if you look at where this becomes large, which is where you would potentially trust it, this also has gap n over 2 pi e, the same as the average Narain lattice. So this is analogous to the BTZ threshold in a theory that only has Virasoro, where the Cardy formula basically turns on and becomes exponentially large at the BTZ threshold C over 12. So, you know, if we had been studying Virasoro, CFTs and we found we found a theory that had spectrum turning on at C over 12, we'd be very excited about that, because that would indicate that maybe it was the dual to pure gravity. So this case is obviously not dual to pure gravity because the symmetries are wrong, but it has a similar sort of structure. And so now to turn to the gravity side of things, I need to briefly review the status of pure gravity. So 3D gravity is dual to a CFT with a central charge C that is much bigger than 1. Assuming the graviton is the only massless field with spin, the chiral algebra in the CFT is Virasoro only and nothing more. A tentative definition of pure gravity is a theory with a large gap. Depending on your taste, you might say that it's a theory where the gap is order C, or you might ask for it to have a gap at the BTZ threshold, C over 12. But certainly it should be a theory where the only perturbative excitations are gravitons. No such candidate theory is known, but there's been a lot of work and progress on trying to construct it. In 2007, Maloney and Witten studied the sum over saddles. So they said, well, if we want to know the partition function of pure gravity, let's just calculate it by doing the path integral. And they did the path integral by summing the known contributions which come from saddle points. That calculation involves first calculating the one loop answer around in vacuum. So that's this thing here. It's the Virasoro vacuum character, or the one loop partition function of the bulk theory. And then we take that and sum over the topologies of the BTZ black hole. So these are different ways. So this is the answer on a torus in the bulk, and this sum over topologies is the sum over all of the ways of filling in the torus. A sum like this over images under SL2Z is called a Poincaré series. There's a number of things we can say about this sum. So first of all, as already noted by Maloney and Witten, the spectrum is continuous and non-unitary. There was a particularly subtle regime here that's non-unitary that was pointed out later by Benjamin et al. So this seemed, so continuous seemed very strange at the time, but in light of recent developments suggests that maybe averaging is at play here. So the non-unitarity can apparently be fixed by additional contributions to the path integral. And the JT random matrix duality suggests that maybe there's an ensemble interpretation. There's growing evidence for this, but so far we don't know how to define an average two-dimensional CFT. So there's been some limits that have been studied, and certainly there's good evidence that this is on the right track, but we don't really know how to do this averaging or what the ensemble would be for 3D gravity. So I would say the status of this is still unresolved. Oh, I think maybe it's on the verge of well, I hope it's on the verge of finally being resolved. I think the hunt is on for the dual of pure gravity in 3 dimensions, and quite possibly that's a problem that can be solved in the near future. But we're not going to solve it now. What we're going to do is replace Virasoro by U1 to the n and try again. That is, try again with the Maloney-Witten approach to calculating the path integral. So first we need a 3-dimensional theory where the one-loop partition function has the correct vacuum character. This is provided by a U1, by a abelian Chern-Simons theory with n left movers and n right movers. Each U1 gauge field gives a U1 current algebra at the boundary. Therefore, the perturbative one-loop calculation in a thermal background, which is on with a torus boundary condition, is the U1 vacuum character, which is this 1 over eta to the 2n that shows up out front in the Narain theory. And this theory is actually one loop exact. So this is the full perturbative contribution on the torus. The tentative definition of the bulk theory is to take this answer and sum it over topologies. So that's the prescription that we're going to use following Maloney and Witten. So we have a Poincaré series to calculate the bulk, which is, as in the case of 3D gravity, this perturbative answer summed over images of SL2Z, under SL2Z. So this Poincaré series is actually a famous Poincaré series that has a name. After you extract some factors, this is what's called a non-holomorphic Eisenstein series. So you extract these eta function factors, then what's left over is the Eisenstein series E, which has been studied in great depth for many years by mathematicians to our advantage. So now using the mathematicians' results on Eisenstein series, you can now do this sum explicitly and read off the density of states. So I won't go through that calculation, but you do this, you can do this very explicitly. You do the sum and you put it into the form of a partition function. That is, you write it as a sum over spins L and dimensions delta. And once you've written in this form, you can read off the density of states of the putative boundary dual. When you do that calculation, the answer that you get is Siegel's measure on random Narain lattices. So this is working. This seemed like when we first saw this seemed like a miracle, and it is a miracle, but it's a miracle that the mathematicians knew about. This is actually a special case of what's called the Siegel-Wey formula, which relates Eisenstein series to integrated theta functions, and we'll hear more about that from Alex. To recap, we've shown that on the torus, n-free bosons averaged over moduli is indeed equal, dual, as far as the torus partition function goes, is dual to this Chern-Simons theory in the bulk. And this holds for any n greater than 2. Although I motivated this by thinking about large n, there's no reason we can't do it at small n as well. We just have to make sure the integrals converge, and that requires n bigger than 2.
Tom, there's a question from Juan.
Okay.
What was the level of the Chern-Simons theory?
So the Chern-Simons theory is being treated perturbatively. So the level does, well, so the level doesn't enter. We can treat it as non-compact. And that, I think that might be one of my remarks too. Okay, so I'll end with just a few remarks about various aspects of this. So first of all, this is not ordinary gravity. We have this apparent duality, at least on the torus. It's clearly not ordinary gravity, obviously. It's this Chern-Simons theory. But to be a little bit provocative, is it really so different at large n? Well, it does have a graviton, sort of. It has a composite boundary graviton because of the Sugawara construction. No, the boundary theory does have a Virasoro. It just is a Virasoro that's constructed by Sugawara. So it does have a Virasoro algebra, and from the bulk point of view, you would say the graviton is composite. So that's one bit of similarity. 3D gravity doesn't have an ordinary graviton anyway, so maybe it's not so different to have this composite boundary graviton. So that should say boundary graviton. Secondly, it has a large spectral gap. As I discussed, the gap is n over 2 pi e. And for comparison, the gap in gravity for BTZ grows with c over 12. Most surprisingly, is that at zero anchor potential, this theory has exactly the same free energy as ordinary 3D gravity. So the free energy of 3D gravity as a function of beta is given by the Casimir energy when the temperature is low. This is like the thermal ADS contribution. And it's given by the BTZ free energy when the temperature is high. So this is the contribution of BTZ. And this answer for the free energy is exactly the same in 3D gravity and in this U1 gravity, or the average Narain lattice. So this was very surprising to me that this theory actually does have a Hawking-Page transition, and the BTC black hole in this theory, by which I mean the S transform of the vacuum state, the modular transform of the vacuum state, it has that BTZ black hole dominates the canonical ensemble and has the same free energy as the BTZ in ordinary gravity. Okay, so they're clearly not the same theory. There are a lot of differences as well, but there are some surprising similarities between this theory and ordinary gravity. In ordinary gravity, this universal behavior of the free energy, this universality, can be understood as a large C version of the Cardy formula, that applies to theories with a sparse light spectrum. That is, to theories either with a large gap or at least to theories that have not too many light states. And a very similar argument applies to theories with the U1 to the N symmetry.
Tom, there's a question from Alejandra.
Yeah.
Hi, can you hear me?
Yes, hi.
Hey, I just have, sorry, shouldn't you have an n log beta? Because you have an m tau multiplying your answer?
Maybe you're talking about the partition function of primaries? This
Well,
is-
the whole partition function, wasn't it an m tau to the n times the Einstein series?
Well, there were eta functions.
Because I thought that there would be like okay.
There's these eta functions out front. So I think what you're saying is right. If we focused on primaries, then we would just be talking about the Eisenstein basically, and we would get something like what you're saying.
Okay, thanks.
Okay, Tom, you also should try to wrap up in 5 minutes.
Okay, sounds good. I will be done. So yeah, so there's this universality in Virasoro theories with a large spectral gap, and there's a similar argument for theories with the U1 to the N symmetry, and the average Narain fits into this universality class. Now, the theories are not the same. The U1 to the N theory has the same number of total states, and that's what we're seeing reflected in this free energy agreement here, but it has far fewer primaries. As I mentioned earlier, when you calculate the density of primaries in Virasoro's theory, you get the usual Cardy formula, which is power law in delta, square root delta, whereas in U1 to the N, you get something logarithmic. But there are a lot of parallels between these two cases. The second comment is that this is not Chern-Simons theory. The proposal is not that it's dual to Chern-Simons theory, but that there exists a theory, U1 gravity, which agrees perturbatively with Chern-Simons, but differs in that it involves a sum over topologies. So this is not the same as Chern-Simons theory. For comparison, ordinary 3D gravity agrees perturbatively with SL2C Chern-Simons theory, but we don't think that these are equivalent. So the idea is that there should be a theory that's related to Chern-Simons, to this other Chern-Simons, maybe in a similar way. Note that since we're treating the Chern-Simons theory perturbatively, we can view it as non-compact for this calculation on the torus. So we're not also summing, when we do the sum over topologies, we're not also summing over non-trivial gauge configurations, like we would if we were studying Chern-Simons theory. Okay, and this is where I'll end. So I just want to conclude by saying that I think we've only scratched the surface in terms of the things that can be calculated in this theory. You know, it's just a free boson, so we should be able to calculate just about anything. And so I hope that we can use this as a toy model, as a testing ground for ideas about averaging and holography. I'd be particularly interested in trying to understand the alpha states and baby universes in this theory. You know, the alpha states the alpha states should correspond to individual realizations of the free boson. So if we understood alpha states, we would have this interesting duality just to the free boson. And it seems that maybe that will somehow tie this back into the old story of the connection between Chern-Simons and Western-Witten theories, although I don't have anything concrete to say about how that would work. So let me just stop there, and thanks everyone for your attention.
Let's thank Tom for this very nice talk. So we are going to take a question, and we already have a question from Juan.
Yeah, so one comment, I guess the theory you are considering in the bulk, you could view it as a theory of induced gravity, right? So you have a bunch of matter fields, which are the Chern-Simons fields, but you still sum over all geometries.
Yes, that's right. I think if it were really induced gravity, I'm not sure it would be, I'm not sure whether we would sum over topologies or not. Maybe that's an additional rule that we're putting in.
Well, I would call gravity any theory where you sum over all geometries and topologies. Here,
Yeah.
you're not putting in any gravitational part of the action. It just comes from the Chern-Simons.
That's right. That's right.
And another question I have is, if you were to do it with finite level K, what is the difference?
Well, so I guess when you say finite level K, what you mean is that when we do the calculation, say on thermal ADS in the original on the background torus, that you want to include the full answer for Chern-Simons theory on that torus.
Right, right.
So you're also summing over the gauge configurations. Let's see. I think if you do that, then if you do that, you definitely get the wrong answer. You won't get the average Narain theory. I think what you get is something. Well, maybe Alex has a better answer to this, because in their paper they discuss this and they say that the theory you get if you do that is trivial. Although I haven't actually tried to do the calculation.
Okay, thank you.
Okay, Alex Bellin has a question.
Hey, Tom. So I got confused about something and your answer for the partition function. I would have thought that just the U1 descendants, the U1 to the n descendants violate the HKS bound, that there's way too many of them. So
yeah, this does not satisfy the HKS. So this does not satisfy the assumptions that you need in order to get in order to apply this paper. What it does satisfy, there's a similar, what I mean is that if you study, you can set up an analogous problem for theories with U1 symmetry, and you can define theories that have a sparse number of U1 primaries, that are sparse in terms of the number of U1 primaries. And then you can apply a similar argument to theories in that class. And then you find the same, at zero angular potential, that will give the same answer actually as the Virasoro one. At non-zero angular potential, the answer will be different.
So you're saying that even a theory that violates the HKS bound can still give that partition function as you wrote it on the slide?
Yeah.
Okay. And I'll need to think about that. And just another question. So this was all for Narain CFTs, but could you comment a bit on how to try to apply these ideas if we wanted to average over the T4 moduli of the symmetric orbifolds of the D1, D5 CFT?
Well, I don't really have anything useful to say about that. I think it would be very interesting. So I don't have anything useful to say, but I will say one thing, which is that Greg Moore wrote a paper about the volume of moduli space for the symmetric orbifolds. And this same formula appeared, where's the formula? This same formula appeared in that paper, but in a very different way. So in that paper, L was like the number, it was not the spin, it was the number of copies of the theory in the orbifold. So I don't really understand why that is, but I don't have anything else useful to say.
Thanks.
Okay, there's a question from Daniel.
Hi, so I'm bothered a bit about the same thing that Juan was asking about. So usually we say in holography that, if you have a global symmetry of the boundary description, it should be a gauge symmetry of the bulk. But here it seems like you kind of, from the boundary point of view, started with the U1 to the n times U1 to the n global symmetry, and you ended up with an R to the n times R to the n gauge symmetry in the bulk. So if that's really the story, then for example, your R to the n times R to the n theory doesn't obey the completeness hypothesis because, for example, it doesn't have states of, charge square root 2 or something like that, which would be allowed by R to the n times R to the n gauge symmetry. Yeah, I'm just a little bit puzzled. Does the relationship between the gauge and global symmetries work differently? And maybe one comment along those lines is that, so in my paper with Hirose, we had a proof of the completeness hypothesis, but we used factorization. So maybe in an average setting, factorization is wrong. I don't know. That could be one way that it works. But anyways, I'm curious if you have any comments about this.
I don't know the answer. I think it's an interesting question. I don't know the answer. I think that I would say that using the non-compact U1 is a trick that we can play to get the right answer on the torus. It's not quite true that the bulk theory is a non-compact U1 in general when you consider higher genus. Maybe that involves going to higher genus, which we didn't do, but Alex and Edward have looked at that.
But can't you test if they're monopole? I mean, it seems like you should already be able to tell. Well, maybe you can't, I don't know. Maybe you can't look for monopoles just on the torus? I mean, you said you don't want to include topologically non-trivial gauge configurations of the U1, right?
On the torus, that's right, yeah.
But why should the rules be different on the torus than something else?
Well, there's a set of rules that applies to all genus, which I think Alex will talk about.
Okay.
It's not quite the same as saying that you consider the non-compact U1, I think.
Uh-huh. But okay, well, maybe I should wait to see what Alex says.
Yeah, we should ask Alex that question because I also want to know the answer.
All right, thank you.
Okay, there's also a question from Edward.
I just have a small comment concerning the last question. I think the lack of completeness should be taken as an indication that the theory has an ensemble interpretation rather than being an honest theory. By the way, as Alex and I showed, you can make the theory somewhat more complete by stipulating the dimension of one of the primaries. For example, you could stipulate that the theory has an dimension n0, or for that matter, nm primary for some n, let's say n0. And then the bulk theory becomes a little bit more complete. Then one of the R's is promoted roughly to an SU2. Anyway, okay. As you further pin down the boundary theory, the bulk theory becomes more like Daniel wanted in his question, more nearly complete. Of course, we don't know the bulk theory in this case in any event, but if you started completely, the more you would specify the boundary theory, the less you would have these nice gravitational theories, formulas for the average.
Okay,
Right, yeah, thank
there's
you.
also a question. Yep. So there's another question from Henry.
Thanks. Yeah. Can you just remind me if you studied whether the case where there's more than one torus boundary? Perhaps this is going to be part of Alex's talk, and if so, what the set of topologies you sum over in that?
So Alex and Edward considered that, and he's going to talk about that.
Great, thanks.
Okay, are there any other questions? Daniel, Edward, you still have your hands up. Do you want to ask something? Okay, so we will continue with the next talk in 2 minutes.